Thank you. So my name is Garren. I'm from Blueprint Technologies, and today we're going to talk about performance potholes and how to avoid them when you're working with Python on Spark. So first, let's start with a little bit about my background. In 2011, Curiosity launched. That's when I started with data. I figured I'd just put some milestones that were clearly very relevant to my own career. So we found water on Mars in 2015. That's when I started with Spark. So I mean, that's pretty similar. And then in 2018, Spark 2.3 brought us stream-to-stream joins, and North Korea met South Korea. So let's talk about an overview. Joe Biden would be very proud of me. I made sure to put in PySparky, not malarkey. Package schmackage, because we're going to talk about how Python interplays with packages. Snoop Dogg makes an appearance here, because we're going to talk about why you need to use DataFrames, not RDDs. And TLC drops it at the end, because we don't want to go chasing UDF falls, yo. All right, so let's start with Joe Biden, eating ice cream. So at the top, we just have a basic overview of a basic Spark application. You have a driver that creates a session, master, cluster manager, that pushes down into all of your slaves and executors. By the way, the link at the bottom, garrens.com/potholes, will actually link you to the full slides. They're already available now if you want to use those, so you don't feel inclined that you need to take pictures or anything. So feel free to grab that at any point. So normally when you create a Spark session, you're going to end up with executors that are running on your slave workers, and those executors are running a JVM, Java Virtual Machine. But with Python, you get a kind of an added twist, because most of what is normally considered Python and PySpark runs actually outside of the JVM, because it has to pickle the data, serialize it, send it on to Python, and it's going to run. That's kind of a problem. We're going to talk about why. But first, let's go into packages. So if you want to install a package, say from PyPI or an egg file, you can go into this is Azure Databricks. It's the same on either Databricks, though. You'd install it, attach it to a cluster. The next part is if you wanted to do this on other managed clusters, you could run just pip install on each of the nodes. That's a critical part, because you need this to run distributed. If whatever you're doing doesn't require distribution, then you're not getting the parallelized effect of Spark. You can also pass in --py files when you're running this at the command line. So now you might be wondering, Scala Packages and PySpark. I know the kitty's really distracting. But it's so cute, I couldn't resist. Yes, you can. So you can use Scala Packages and PySpark. That's one of the most beautiful things, because there's a lot of really powerful stuff. So for example, if you go to spark-packages.org, this is one of the packages that I use pretty frequently, natural language processing, Spark-NLP. You'll find it there. It's made by John Snow Labs. Another place that you can reference for when you have to put in the Maven coordinates for when you actually want to tell it to load a package is mavenrepository.com. So this is the actual syntax that you'd use to build your session here. If you use the session building, you have to make sure that you do this before you do your get or create call. Otherwise, it won't actually load that. And with the --packages, those are interchangeable. So you could run either or of those. They'll do the same thing effectively. So pandas. A lot of people like to use pandas. I mean, I'm sure that this is a common trend in Python in general. Everybody loves pandas. And what's not to love? So one of the things, though, about Python and Spark is that there's a cost to doing some things. So this looks really innocuous, because you're asking Spark to just send the data back. I want to put it into a data frame, into a pandas data frame, that is. But it's not innocuous. It forces the evaluation, so Spark is lazily executed. That means it's waiting at every moment. It's waiting for you to actually tell it to truly do something. It's a lot like me. I'm just going to sit there and not going to do anything until I really have to. So it forces the evaluation. You don't want to force evaluation of things in PySpark, or in Spark in general, unless that's your true intent and you actually want it to finish all of its processing. So everything has to run. It's going to collect all of those results to the driver machine, so whatever you have distributed across your 100-node cluster, all of those, whatever results are in that data frame are going to have to come back to the driver. That means network, CPU, memory, disk, all of that. Well, disk won't be involved yet, but it's all then going to have to be serialized into Python's memory on that single driver machine. So be careful about using things like 2pandas. So we're going to talk about, these are the three methods, these are three primary methods that have some real caution tape around them, because they all three require memory. However, there are many ways to get at how much memory is going to be used when you're calling these methods. For example, you can do df.cache.count. This is going to be a forced eager evaluation, where it's just going to tell you how much memory you're using when you check the Spark UI. So now we know that this particular data frame has 3.1 kilobytes. I mean, that's going to blow out machines from like 1975. Don't try to use get storage, RDD storage info, because that method is not supported in PySpark. I know, dumb. But don't worry, I got another fun way that you get your memory, because maybe the whole point of this is you don't know how much memory you have in your data frame yet. So one of the ways that I would really recommend going about this is actually taking a sample. So you do a sample of, say, 1% of your data. Now you do a cache and a count. And so now it's going to eagerly evaluate, and it's going to be it's going to be intense, because it is going to be doing a random sample of the data. But at least in this case, you get an idea of kind of what you're working with. So this is not something you want to be using in a production application unless you're accounting for the fact that it's going to run through your whole process at the same time. One thing that I do recommend really avoiding is size estimator. It's very easy to fall into the trap of believing that that's a really good estimate for what you're going to use, but it's notoriously not always the most accurate, and more importantly, in order to use size estimator, you actually have to use the Java, the RDDs. So the RDD, you have to convert it to an RDD and go through the JVM to do that. So there's actually kind of a hack. It's a really cool Stack Overflow answer. So if you find that, and it's fun, I can show you it if you guys really care later. It's great for what used to be helpful. It used to be more useful, but now it's just not as relevant now that we use data frames more regularly. So what's up, Snoop Dogg? So before Spark 2.x, basically 2.0, the main entry point was Spark context. You had a Spark context, which was the SC variable. You created a resilient distributed dataset, RDDs, and you do something like sc.text file. You also use dstreams, which are RDD-based, and mllib. However, once Spark 2.x hit, Spark session became the main entry point to Spark, and that's now in the very aptly named Spark variable. The preferred APIs shifted as well, quite substantially, to data frames for Python and data sets for Scala and Java. Any Scala lovers out there, you'll be pleased to know that you get a lot of really cool stuff from just you have data frames and data sets available to you. It's kind of cool thing. Structured streaming now took over for dstreams, and Spark ML, or Spark likes to call it mllib. It's a little bit confusing because it is called mllib sometimes, but it's data frame based. That took over for the RDD-based mllib. So this was a little O of pies that I had come up with previously because I really just found it convenient that it all worked out for me. So what that stands for is optimized, parallelized, immutable, encoded and strongly typed, but we're in a Python session, so I have to get rid of the encoded and strongly typed. So we're going to end up with OPI, but that's still better than ON or ON log n, because those things are only for Scala and Java. What? All right, I missed that joke. So optimized, what do I mean when I say optimized? Tungsten, so Project Tungsten was taken on to really improve memory management, binary processing, cache-aware computation, and code generation. Catalyst is even more frequently talked about because this really kind of serves as a core layer of optimization, and it's what makes DataFrames really optimal as opposed to RDDs directly. You get the analysis through the abstract syntax tree, logical planning, physical planning, and code generation. And you'll see that both Tungsten and Catalyst integrate code generation because code generation really makes it significantly more efficient. So here's kind of an example of, or it's kind of a flow of how Catalyst works. You've got your syntax tree coming in, data frame, data sets, goes through a query planning phase, and that query planning phase through the optimized query plan takes into account the logical plans and optimizes as it's going, the physical plan, and finally that ends up, now because of the cost optimizer, the cost CBO, yeah. You get final physical plan that comes out of it. So what this actually looks like is if you have a SQL statement that really naively is you're trying to do a join of two tables, then you have some filtering mechanism, and then you're finally selecting out, projecting the final values. What that becomes is Spark is going to go down and make it more efficient. So if you look all the way from the bottom, only programmers would build a tree from the bottom up like this, or a top down. It's kind of an awkward situation we have. So we're going to scan the table, but now you'll see that we only grab the T1 ID and value at this point, at the right here. So we're only going to grab the two values that we care about. So we're automatically going to save on some processing and all of our resources there. Then we're going to scan the second table, only grabbing the value that we use from that table as well for the join. And since we already know what our filter criteria look like for that second table, Catalyst will optimize that as well, and it'll do push-down filtering. So that now when we do our join, it's only going to take place on the ones that are actually going to eventually have a match regardless. And finally, we're going to project out the same values that we had before. Parallelized, that's just, we have underneath all of it all, underneath data frames and data sets are RDDs still. It's just going through that optimization layer that I was just talking about. And those actions result in a job. Job has stages. Stages have tasks. Tasks are the lowest level of individual. Sorry, I broke ahead of myself. So a partition is a logical split of data. It maps to HDFS or Cassandra partitions, and it's up to the executor's memory limit. Tasks are the individual unit of execution. So we get some really happy minions because they're doing lots of work all together. Immutable. I previously had a picture to describe this, but it always takes the perfect intro to get it going well. So instead, we'll just go straight into code instead. So this is just Python. Normally with Python, if you create a dictionary, you have foo and bar, and then you modify, you change the value of the key from bar to quux, it works fine. There's no problem with that. Spark doesn't like that. You have a data frame, and it's foo to quux. You try to modify the value, or you try to add something, and you're automatically going to get a type error because it doesn't support assignment, so it's immutable. But if this is just a basic example, I guess, of if you wanted to create that value, you'd provide the with column and print it out. So TLC makes an appearance for some UDF falls. So this is kind of a normal example of how you might come from Python to Spark. You need this UDF, and I've seen this many times. This is why I put together this talk to begin with. You want to create a UDF. You want to create some custom code that Spark doesn't support natively. And so you create this UDF that is going to take in, sorry, let me make sure that I'm showing you. It's going to take in the value is t. It's going to do string format time. So all you're doing here, what you're doing here is taking in a timestamp that's in like a year, month, day, hour, minute, second. And it's going to take that and it's going to convert it into epoch seconds. or second since epoch, I think would be the better way to say that. And then it's going to just cast it as an integer. So that's all you're doing. It's pretty simple stuff. It's pure Python. And so this is the way that you'd ultimately create that UDF, is you'd have your definition here. Then you'd use it by just saying, I want to select out that value and use ts.toEpoch and provide your actual column, and then do a distinct count, because that was just what I was doing as an example. So that's going to run, it's going to function, and you may not know any better, but this is a performance pothole, because we can do this in the JVM and get much faster performance by just using the Spark SQL functions. So that's in the PySpark.SQL.functions namespace. And so now, instead of using our ts.toEpoch, we can use f. F is just the casting of functions to a big letter F, like my grades in school. So this is kind of what it looks like if we were to run an explain on both of the different choices there. We had the Python version with the UDF, our Python UDF, and so now you see that it's going to project, and it's just selecting out the Python UDF value as a lambda. And then this is the version that we get when we use the Unix timestamp function. So they both look similar. You wouldn't really notice a difference per se. But I think you might notice the performance is ever so slightly better when you use Spark SQL as opposed to a Python UDF. Now, I'm no mathematician, but I do know a little bit about performance, and it's the equivalent of burning money. So what you end up with is, why burn money when you can make it 30 to 40 times faster and have to actually do less work, because now you don't have to write that UDF in the first place. And I put a pickle there for a good reason. It's because you're going to have to pickle all that data and send it off to Python. So if you think that that's just some random picture, it's not. But let's talk about the next part, that PySpark really got a nice, sweet upgrade when it came to Spark 2.0. As soon as 2.0 hit, it's just a lot of things took off, because it used to be, before 2.0, you had data coming in through Python, and you'd go into RDDs, and you'd execute everything inside of that, inside of Python, in those interpreters, and that was inefficient. 2.0 hit, and you got a new access to the DataFrame and Dataset API, or DataFrame APIs, and that became the primary point of contact. However, one part of that is you still were using Python when it came to UDFs. UDFs were still being run in Python, row at a time. But as of 2.3, which just came out in February, earlier this year, late February, you no longer have to do that. And that's because of Pandas UDFs. So Pandas UDFs take values from Spark in the JVM, use Apache Arrow, and then Pandas ultimately to vectorize the results so that now you can run UDFs and get performance that's much more commensurate as if you were running on the JVM. And this is a huge, huge improvement that I really can't state enough. I mean, all you have to do is really look at the CDF function, and you go from 242 seconds runtime using the old style of UDFs, and now using Pandas UDFs, that gives you 1.1 seconds. So let's see a short little example of what this looks like. If you were to create a UDF normally, you'd have all these different function calls. You'd say you have a UDF, it returns a double, and then you'd pass in your stats, norm, CDF. But if you can see, I highlighted the version, the changes that I would propose making to that. So that now you're importing Pandas UDFs, you're then telling it you want to pass back a double as well, and you're telling it that it's a scalar. So the other option is a grouped map, I believe. I'm not showing that here, but it's definitely something we can talk about or look into. And finally, it's a slightly different call. So that's another part to consider with Pandas UDF specifically, is you're no longer doing things row at a time, so now you're working with a Pandas series, and it's going to run these functions so that you get the vectorization and the really good performance boost. And it's still the same functionality that you get in the end, just faster. So this is what it actually looks like. I think I'm running a little bit early, which is cool. So rehash, Apache Spark plus Python is as good as Py, but done wrong, it's a pie in the face. My work here is done. And remember to rate this. If it's horrible, that's okay. You can rate that. Thank you for not falling asleep. Any questions?